Millsaps College, who will talk about Ramsey theory. Please.
Thank you very much. I actually glanced back at my CV. I believe this is my 8th time speaking at CANT, and I've attended several more besides that. So CANT is a big part of my schedule every year, and I'm very thankful to Mel for keeping it going and also continuing to invite me to speak. And as I mentioned in the intervening moments there, this is the second time in a row where I'm going away from my usual direction, which is Fourier analytic methods, circle method in arithmetic combinatorics, and instead highlighting some work that I've done with undergraduate students at Millsaps College, which is in Jackson, Mississippi. So this past summer, right in that sweet spot, it was in July of 2021, between sort of the Delta and Omicron waves, we were able to actually gather for 5 weeks in person. And the subject matter was Ramsey theory and arithmetic combinatorics. And I started with the basics, and the students led us toward some very interesting questions much closer to the surface than I anticipated. So starting with the basics, Ramsey's theorem says that if you color the edges of a complete graph with some finite number of colors, then you can find arbitrarily large complete subgraphs that are all where the edges are all one color, provided the number of vertices is sufficiently large with respect to both the number of colors and the size of the complete subgraph that you want. So the threshold at which that pattern becomes guaranteed is what we call a Ramsey number. I've specifically called these diagonal Ramsey numbers. What I mean by that is the size of the complete monochromatic subgraph that I want doesn't depend on the color. It's the same for each color. So the kind of original version of this is what's sometimes called the party problem. So how many people do you need at a party before you're guaranteed to have either 3 who all know each other or 3 who have all never met? So you can translate that to a graph setting by saying, let the vertices be the people and color the edges with 2 colors depending on whether the pair know each other or not. So then the pattern that you're looking for is just a triangle that's all one color. And this picture is sort of a lower bound, like a counterexample, because here's 5 people. And if you notice, every triangle has at least 1 blue edge and at least 1 red edge. So if you want to guarantee that pattern, you would need at least 6 people. And you can prove with a quick pigeonhole argument that 6 is indeed enough, but which we'll discuss in a minute. But famously, these exact thresholds are very difficult to nail down. In fact, in this diagonal setting, there's only 2 more that are known at all. So if you still have 2 colors and you want a complete graph on 4 vertices instead of just a triangle, you need 18 people. But if instead you raise the number of colors from 2 to 3, then 17 is enough. And there are a few off diagonal cases, like if you want a blue triangle or a red K4, you only need 9 people, things like that. So that's what I mean by non-diagonal. There's a handful of those that are known, but as far as the diagonal cases, this is literally it. Okay. But most of my interest is in additive combinatorics. So usually when I'm thinking of Ramsey theory, I'm thinking of it in an additive setting, like Ramsey theory on the integers. And usually when I'm stating Ramsey's theorem, it's to transition into something like Shor's theorem. So Shor's theorem says, instead of coloring the edges of a graph, what if you color the first n positive integers? What this says is you can always find as many integers as you want, such that all of those integers and their sum are all the same color, provided n is sufficiently large with respect to the number of colors and the number of variables in that equation. So the classical version is where k equals 3. So the equation is just x plus y equals z. So you want 2 numbers, not necessarily distinct, and their sum to all be the same color. So here's my lower bound counterexample in this setting. What this is a coloring of the numbers 1 through 13 with 3 colors, red, blue, and black, such that if any two numbers are the same color, their sum is a different color. And that includes the doubles. So like 2 is a different color than 4, etc. So that shows that to guarantee that pattern, to guarantee a monochromatic solution to that equation, you need at least 14 if you have 3 colors. Not so easy to prove that 14 is enough. And like with the Ramsey numbers, there aren't that many specific thresholds actually known. So this list is all for k equals 3, so all the x plus y equals z case. The most recent one was 5 colors, and that was done by Hula in 2018. And it was done with SAT solvers, and the proof was 2 petabytes in size. So it's one of the biggest computer proofs that there has ever been, to show that if you color 1 through 161 with 5 colors, you will have a monochromatic solution to x plus y equals z, but also there exists a 5 coloring of 1 through 160 without such a solution. Okay. So what did we actually talk about? So I mentioned that you can prove that party problem up or bound with a pigeonhole argument pretty quickly. So it's very classic, but I still want to do it because I can do it in basically one line with a picture. So 6 people at a party. It's you and 5 other people. Break those 5 other people into the 2 groups, the ones you know, the ones you don't. By the pigeonhole principle, the larger of those 2 groups has at least 3. Color the edges from you to those people blue. So now you have you, and you have at least 3 blue edges coming out of you. Case 1 is some edge between those other 3 people is blue. So you have a blue triangle. Case 2 is none of the edges between those 3 people are blue, which means you have a red triangle. Either way, you have a monochromatic triangle and you're done. So that is the entirety of the proof that 6 people is enough. And this exact 2-case analysis generalizes to a recursive upper bound for these 2 color Ramsey numbers. So this is now, we're into the non-diagonal setting, right? You either want blue K1 or red K2. Well, if you want that the previous Ramsey numbers in those respective colors, and you want to count how many vertices you need, well, you need to count yourself. And then you want to make sure that you have at least that many in one of the 2 colors. You don't actually need to add the numbers together. You can kind of cash in on the way the pigeonhole principle works, subtract 1 from each of them, and then add 1 at the end to trigger the pigeonhole principle. So at least one of those 2 groups will be the size that you want it, and you can do this case analysis. So what that does is notice the 1, -1, -1, +1 all cancels out, and you get almost what is exactly like a Pascal's triangle relation. And so this recursive upper bound leads to an explicit upper bound, which is this binomial coefficient. So if you want either a red KK1 or a blue KK2, this binomial coefficient is always enough. Now, I've written the word sharp here. I want to be clear what I mean by that. It is absolutely not sharp in the sense that the Ramsey numbers are not equal to these binomial coefficients. Even in small cases, you can do like parity arguments to do better than this. What is sharp, though, is if I ask the question, what explicit bound is yielded by this recursive bound, then it is exactly this one. It's a perfect, it's like a lossless passage from a recursive bound to an explicit bound. Okay. What if you had more than 2 colors? The pigeonhole principle works the same. But now the -1s don't exactly cancel out. So you have this term floating out here, minus r minus 2, where the r minus 2 is greater than or equal to 0. In several sources that we found, we saw this quoted explicit upper bound, and it's a very natural generalization. It's just replacing the 2 with r. And what this is here is a multinomial coefficient. instead of a binomial coefficient. It's like a generalized Pascal's triangle relation. And in particular, that gives this pretty easy to write down upper bound on the diagonal Ramsey numbers. However, that comment that I made about the passage from recursive to explicit being lossless, that is no longer the case with more than 2 colors for multiple reasons. Number one, the R minus 2 is no longer 0 if R is greater than 2. And this induction argument to get this explicit bound ignores that term. But even more important, Ramsey numbers should always ignore 2's. And what I mean by ignore 2's is, if I look here, R sub R of K1 through KR minus 1 comma 2. A complete graph on 2 vertices has another name. It's called a single edge, right? It's literally just an edge. So the only way to avoid a monochromatic complete subgraph in that Rth color of size 2 is to not use that Rth color at all. So that actually reduces you back to the case of R minus 1 colors. So if you're going to have a nice explicit formula for upper bound for these Ramsey numbers, that upper bound should sort of satisfy this type of relation. And this one does not. If you introduce a new color with K sub R equals 2, it will actually raise the value of that multinomial coefficient, potentially a lot. So, whoa, sorry about that. So an example is, it's a pretty classic exercise to show that the Ramsey number for triangles with R colors is bounded by something like E times R factorial. But this formula up here does not give you E factorial. It gives you something much bigger. Okay. So the question sort of becomes, what is a way to capture the strength of the recursive bound given by the pigeonhole principle in a more efficient way with an explicit upper bound? So here's one more example. If you have 3 colors and you want a complete graph on 4 vertices, if you literally just iterate the recursive bound all the way down until you get down to 1 color, then it gives you an upper bound of 272. That's with no other considerations other than the pigeonhole principle. But the formula I quoted, which is the most classically quoted explicit upper bound, gives 1,680. So, it's off by a little bit. And the more colors and the larger patterns you're looking for, the further apart they get. So can we do any better? The answer is yes. So I'm giving what I'm calling a sampling of results here. These results are joint with me and all 6 of my student co-authors. That is Vishal Balaji, Powers Lamb, Andrew Lott, Dhruv Patel, Sakshi Singh, and Rose Ward. And we proved a lot of things. I've decided to quote here the simplest result and sort of the highest tech result. Okay. So the main difference between this formula and what is usually written down is these 2's are replacing what were previously 1's at the expense of a term out here that is uniformly bounded in both R and K. It's less than or equal to 4. Okay, so roughly speaking, that beats the bound I wrote on the previous slide by about a factor of R to the R. Now, it depends on what your perspective is, whether you consider that to be significant. But it is certainly something that tends to infinity pretty quickly with the number of colors. I should also say that the idea that the previously documented multinomial coefficient bound is wasteful is not a new idea. I found it mentioned in a book, like a book chapter of Graham and Rodel, but nothing like this exactly had been written down. This still ignores that R minus 2 term. It really is just a much more careful induction. But by taking into account that previously ignored R minus 2 term at the end of the pigeonhole principle upper bound, we were able to get something even better. this is an asymptotic bound. So you have to multiply all this by something that 1 plus little o of 1, where the little o is as r tends to infinity. The reason is because there's all kinds of Stirling's approximations going on here. It was very tricky to keep track of the impact that that r minus 2 had on the pigeonhole upper bound. But what was interesting is it's not like a second order term. Notice we have subtracted a positive proportion of what we got when we ignored the r minus 2. So this constant that's around 4 has been reduced to something, that's less than 3. And I've mentioned some of the previous work that went into getting this as far down as we could. So again, this is not claiming that this is in any way a sharp upper bound on multicolor diagonal Ramsey numbers, but it is an explicit bound that captures the strength of the pigeonhole principle considerably better than anything that had been written down before. To pivot a little bit, I mentioned my interests tend to lie in the additive setting. So if we pivot back there, one of my students, Andrew Lott, posed this question to me. What if we tried to do something like Schur's theorem, but in integer lattices in higher dimensions instead of just integers? For example, what about monochromatic solutions to x plus y equals z in colorings of this is 1 through n, the first n positive integers squared. And I thought, well, that seems like a nice idea, but if it's interesting, it's probably been thought about before. And what we figured out pretty quickly is, as stated, it's not interesting. Because if you had a coloring that didn't have any monochromatic solutions, you could of the integers, you could just color the grid based on the first coordinate, and you still wouldn't have any monochromatic solutions to x plus y equals z. So think of this as 1 through 4 squared. There's no solutions even in the first coordinate, so there's going to be no solutions in the grid. However, if you know there's a solution in the one-dimensional setting, then that same solution will show up on the diagonal. So in this case, 2 plus 3 is 5. And that shows up in the grid as 2, 2 plus 3, 3 equals 5, 5. So the threshold where the monochromatic solution becomes guaranteed is exactly the same as it was in the one-dimensional setting. But when I look at that upper bound, what I said to myself was, well, yeah, but that's sort of like a degenerate solution. It's all happening on a line. Maybe we could insist that we have a solution to x plus y equals z in the integer grid, but we insist that x and y are linearly independent. So I'm going to quickly sketch a proof here, just in the case of x plus y equals z and 2 dimensions. It's going to use Ramsey's theorem. If you're familiar with the proof of Schur's theorem from Ramsey's theorem, this is essentially it. The only difference here is I'm forming my graph with vertices that are integer lattice points along the parabola. So v sub I is I comma I squared. So I form a graph by the edge connect. So I color 1 through n squared. And then we connect each of these vertices on the parabola with an edge, and we color it based on the assigned color, of the difference vector. Okay. So for example, we have a vertex at 2, 4 and a vertex at 3, 9. We color the edge between it with the color assigned to 1, 5. This sentence here should actually be edited. It should say each pair of these edge vectors are linearly independent. Each pair that share a vertex, each pair of edge vectors that share a vertex are linearly independent. So by definition of this Ramsey number, there is a monochromatic triangle in that graph. But if you look at what a monochromatic triangle means, the colors are assigned based on the differences, and VL minus VJ plus VJ minus VI equals VL minus VI. So there's your X, Y, and Z with x plus y equals z, and x, y, and z are all the same color, so you win. The linear independence is guaranteed by the fact that I chose the vertices along this parabola. And that proof generalizes quite nicely. So it generalizes for any dimension and any number of variables. So as long as your n is at least the r color kth Ramsey number to the d, where d is the dimension you want, minus 1, then every r coloring of 1 through n to the d has a monochromatic solution to the Schur equation in k variables, where the first d of them, because you're in d dimensions, that's all you could hope for, the first d of them are all linearly independent. So it's exactly the same as what I just outlined, except the vertices are sort of on this monomial curve instead of just a parabola. It's like I squared, I cubed, up to I to the d. And we actually struggled a little bit to show that the vectors we needed to be linearly independent were. It was very, easy algebra in the dimension 2 case. It turned out that what we really needed in the higher dimensional case, if you put the vectors into a matrix, the determinant of the matrix is exactly equal to a Vandermonde determinant, which is non-zero because all the indices are distinct. The other thing you could ask for is you could ask for small cases, like small case thresholds, like we had with the Schur numbers in higher dimensions. And my students, Andrew Lott and Vishal Balaji, they actually got in touch with people at the University of Mississippi in Oxford and got access to one of their supercomputers. And so I'm just going to end my talk with some pictures that Andrew created. So here's the first picture. This is a 2 coloring of 1 through 6 squared. Now remember, there will be a solution, a Schur triple, a solution to x plus y equals z on the diagonal. For example, 1 plus 5, 1 plus 5 equals 6. But there are no solutions with x and y linearly independent. So that's what we mean by a 2 coloring of 1 through 6 squared with no non-degenerate Schur triples. But moreover, what Andrew was able to determine with a SAT solver is that no such 2 coloring of 1 through 7 exists. So 7 is the answer in 2 dimensions with 2 colors for x plus y equals z. He was able to get the exact answer for 3 colors as well. This is a 3 coloring of 1 through 17 squared with no non-degenerate Schur triples. Remember, that means that if x and y in this picture are linearly independent and the same color, then x plus y will be a different color. Okay? But no such 3 coloring of 1 through 18 exists. He was only able to get a lower bound in the 4 color case, but it's a cool picture. So this is a 4 coloring of 1 through 48 squared with no non-degenerate Schur triples. We do not know if such a coloring exists for 1 through 49 or not. And what Andrew likes to highlight, which I like as well, is that there is some symmetry to this picture, but it's not perfect. It's sort of a little bit off. So it's an interesting picture. Yeah, so I think that's where I'll stop. Thank you.
Oh, thank you very much, Alex. Very nice. Any questions for our speaker?
Alex, I wondered if you've considered rainbow configurations. So where you mandate that they're all different. And I know a lot of work has been done on this, but just curious.
I haven't specifically, but Andrew's a very enthusiastic undergraduate. So if I tell him anything, he'll start thinking about it right away. So I'll let him know.
Other questions for our speaker? If not, then thank you again, Alex.
Yeah.
And the next talk is in about 5 minutes.